Make it look better. Okay. If you looked, you might have noticed the homework's not up. I'm going to try to get that done today. I might work on it while the stars are playing. Sometimes it's just so stressful. You're like, I can't watch this. But you still watch it, but you need something else to like occupy your brain for a second. But yeah, I'll get you the homework very soon. We will get the first lab sometime very soon. I just have to figure out how to do it for the online students, or maybe find an alternative for them, like a virtual lab. But I don't know where I could find a virtual lab, like for minerals and rocks. So we're just going to start to lecture over the next chapter, which is rocks. I think previously maybe the second test was chapter 1 through 3. I might still keep it that way. I might shorten it to chapter 1 and 2, because chapter 3 we get into water, and I think that might go better with a different set of chapters. Let me actually see. Come on. Intro. Let me actually change the slideshow. What am I looking for here? Setup slideshow. Yes, browse by an individual. Okay, that'll work better. But if we go to here, yeah, chapter 3 and 4 kind of go together. Water in the Earth's surface and glaciers and deserts, which we'll go through glaciers and deserts pretty quickly. So I might make those a separate test, and that will get y'all one more test grade, which will actually help kind of even things out and make each test a little bit less, worth a little bit less, and not quite as important to your grade. So I might do that. That seems like an okay thing to do. We'll see though. So, also, the Lockdown browser is now installed on all of your Chromebooks, and so probably sometime this week, I will go ahead and like write up an email, and maybe we'll make sure that all of that is working here in class for y'all, so we know that it's working for the online students at home too. Okay, so today we're going to start with rocks. Remember, at the very beginning of the minerals section, we talked about minerals being the building blocks of rocks. And so as we talk about each of these different rocks, remember that they are made up of individual little minerals. Almost always there's a mix of minerals to go along with one of the rocks. And we're going to talk about 3 different settings in which the rocks are made. And I'll let the PowerPoint kind of get to it as we go through. So, what processes can transform a rock from one type to another? So these are the 3 different types of rocks: igneous, sedimentary, metamorphic. We will kind of get to these, but this is the main question that we want to answer, is what makes a rock an igneous rock, what makes it a sedimentary, what makes it a metamorphic, and how do they go back and forth between these. This is maybe not the best visualization of the rock cycle because it's just linear, and the rock cycle is actually very, very complicated. So you'll see that in a different slide. So the rock cycle describes interactions between components of the Earth system, the origin of igneous rocks, sedimentary rocks, and metamorphic rocks, and how they are connected, which they're very much interconnected. Remember that when we talk about the rock cycle, pretty much any rock can be transformed into any other type of rock at any time, if the conditions are right. And so there is no one set way that a rock goes through the rock cycle. There might be some that are more common than others, but it can really, it's like a wheel more, where any part of the wheel is connected by spokes to the center and to the other parts of the wheel. So in general, when you have a wheel, you got to have some place to start. We're going to start with igneous rocks, and say that the rock cycle begins with magma, because ultimately that's where we began at the very, very beginning of the Earth. Was everything was molten and hot as the Earth was starting to form and cool down, and so our very, very first rocks were igneous rocks. And so igneous, which they don't have the term up here, Igneous sounds like I don't know if it's Latin or some other old language, but igneous sounds like ignite. And so igneous literally means from fire, I believe. And so remember that igneous rocks always come from magma. That's the number one way. That's the only way really they form, is they come from melted magma. That magma will cool either in the surface and stay magma, or it will become lava through a volcano or a fissure, and it will come to the Earth's surface and it will cool much faster. So think of it kind of like, this is not a good thing to do. I wouldn't recommend this, but think of this kind of like making muffins at home. Anybody ever make muffins or like cupcakes? You don't let your cupcakes cool in the oven. You don't just like turn the oven off and leave your cupcakes in there. They're probably going to burn. But the reason is, if you leave them in the oven, they're going to continue to be hot for quite a while. If you ever come back to the oven like 30 minutes after you turned it off and open the door, it's still hot in there. And so magma rocks that stay underneath the Earth's surface and don't ever come out as lava take a very, very long time to cool because they're essentially still in the oven. Even if they've moved away from the heat source, they have a lot of rocks surrounding them, and that's a good insulator, and it helps hold that heat in. Whereas lava comes out to the surface, and it's exposed to the air, it's exposed to water sometimes, and it will cool very, very quickly. Might be 10 years or 100 years, but that is a quick time as far as magma and lava is concerned. So we will talk about the processes that lead towards eruption of magma. It's more just essentially density and heat. Hot things rise, just like convection in a coffee cup. Hot things are also less dense, and so they're more likely to rise, which is part of that rising. And so they will rise to the surface, and if there's a path for them to get to the surface, they will come all the way through and erupt as a volcano or as a fissure. The magma that does not have a chance to come all the way up to the surface will get trapped underneath the rock layer and will slowly cool over time. And so we're going to look at the minerals and what that means for them as that cooling occurs. So igneous rocks that are exposed at the Earth's surface undergo weather. This leads us to the second part of the rock cycle, which is the sedimentary rocks. So you have to have weathering in order to break down an igneous rock and turn it into sediment, and then it can be transported through erosion. So remember, we talk about weathering and erosion often like they're the same thing. They are kind of two parts of the same process, but they are different. Weathering is the breaking down of that rock. Erosion is the movement of that rock to a different location, which almost always happens, but to different degrees. Sometimes your little sediments are moved hundreds of thousands of miles. Sometimes they're just literally moved from the top of a mountain to the bottom of a mountain. They don't go very far at all. It just depends on the situation that you have. Know that because gravity, almost everything is slowly working its way towards the ocean. It wants to go downhill, and the farthest point you can go downhill is to sea level, and then below sea level down to the basins of the ocean. And so some sediment does get stopped and does form into a sedimentary rock before it gets there. But in general, all sediments are trying to make their way to the ocean because that's just the way that gravity likes to do things. All water is trying to make its way to the ocean. It may get stuck in a lake at some point in time and remain there for as long as it can. But all water wants to make it back to the ocean, to its home. Okay, so deposited sediment. So when you have weathering, it breaks it down into little bitty pieces that we call sediments. At some point in time, the sediment's going to stop. Whether it's in the ocean, in a lake, in a valley, it's going to stop somewhere and get covered up with other sediment. And eventually it gets compacted. So you have something on top of it that's pushing it down, that's pushing all the little pieces together. That's just one part. Before it can become a rock and undergo lithification, it has to be cemented. So you need some sort of liquid, usually water, that has a mineral-rich content. It's going to run and flow in between it, and it's going to kind of glue everything together. So you have to have sediments. They have to be compacted because they can't be kind of like loose sediments like the beach. Sand on the beach isn't considered a rock. It's considered just loose sediment. But at some point in time, if you compact it down and you glue it together and you have that cementation, it can become a solid sedimentary rock like a sandstone. So that is the second part of the rock cycle. We have igneous, which is melted rocks that come from magma lava. We have sedimentary rocks, which come from weathering, erosion, and then lithification. And then we have metamorphic rocks, which when I first started teaching this class, my brain doesn't remember when things happened. And so I'd always make this reference to The Metamorphosis, which is a book by Frank Kafka, which I just assumed that all of you had read because it's like a very important literary book. But turns out that's a college book, and none of you have read. Has anybody read The Metamorphosis? When you do read it, it will stick with you for the rest of your life. And anytime you hear the word metamorphosis, you'll be like, oh, like Kafka. Because it's a terrible story. Like most great literary works, it's just a terrible, make you depressed story about a boy who wakes up one day and he's been transformed into a giant cockroach. Literally like a giant, 4-foot, 5-foot cockroach. And his family hates him, and I believe they end up killing him. And it's just a very sad, Kafka-esque story. And you read it and you're like, I hate you, English teacher. Why did you do this to me? You made me read this story. So now every time I teach metamorphism rocks, metamorphic rocks, I think of Kafka and the metamorphism, and it's not a good day. So whenever you read that, think of me and think of metamorphic rocks, and maybe your day will be a little bit better instead of just thinking about the story that you have to read. So metamorphism, this does not always happen. One thing that does always happen, all rocks at some point in time started in the igneous phase through melted magma, even if that was a very, very, very long time ago. For a lot of rocks, not all of them, they will be exposed to the surface and will undergo weathering and erosion and become sediments and end up as a sedimentary rock. Only a small portion of rocks end up undergoing metamorphism. So you have to have a good enough amount of heat and pressure, but not to melt it all the way. It says melt the rock and generate magma. That's not metamorphism. If you go back to magma, it's igneous rocks again. You've gone back to the igneous cycle. If you have enough heat to heat the rock up and have it change without melting and going to magma, then you have a metamorphic rock. And so metamorphic rocks have heat and pressure, which I think this is kind of small on this board, and this board doesn't have great resolution. But it does say right here, heat and immense amount of pressures give you a metamorphic rock. And we'll kind of look at what happens to metamorphic rocks and how they change when we get to that section of the PowerPoint. But here's your rock cycle. And you can see it is a cycle. It does kind of go around. But note that you have arrows kind of going anywhere and everywhere in the rock cycle. And so you can go from any one point in the rock cycle to any other point pretty easily. And that happens sometimes more often than the arrows on the outer edge. Notice even metamorphic rocks can come back around and be remetamorphosed without going to any other section. And so they're kind of interesting. And actually, I'll try to remember this week, I have a really, really cool metamorphic rock that I got from New Mexico. And I'll bring that in and show y'all kind of why it looks so different. So yeah, this is a rock cycle. Let's start at the very beginning. You have magma. Sometimes it comes to the surface and becomes lava. It has to cool. If it's still molten, it's not really a igneous rock yet. It has to undergo cooling. It has to get crystals. Your minerals kind of have to come out in a certain way, and then you can become an igneous rock. From igneous, you're sometimes exposed at the surface. There's a huge amount of igneous rocks that will just probably always be under the surface and never really be exposed and weathered and eroded, and they'll just stay igneous rocks for a very, very, very long time. But a portion of them get exposed to the surface. They go through weathering and erosion, compaction and cementation, and they become, well, before they undergo compaction and cementation. They have a sediment stage. They become sediments, loose sand, loose dirt, soil, all these different things that are just kind of loose pieces of what used to be igneous rocks. So they will become sediment. Some sediment, not all, but probably most, will eventually get covered up by other sediment. It will get compacted. It will get cemented together, and it will become a sedimentary rock. When you think of sedimentary rocks, think of like the Grand Canyon. Pretty much everything you see in the Grand Canyon is a sedimentary rock. You could also think of like the white limestone that we have here in Texas that makes up most people's driveways. That's an oceanic sedimentary rock. And then if you have enough heat and enough pressure, which is probably pretty rare, metamorphic rocks don't make up a huge part of the rock cycle. But if you get enough heat and pressure in the right situation and you don't have melting occur, you can get a metamorphic rock, which is very unique and very nice. If you happen to have like a granite countertop and it has a bunch of like swirls and whirls and kind of looks like a design or pattern in there, you might have something that's a metamorphic rock and not actually a granite. And then you can go all the way back around and have melting. You can melt from pretty much any point. Sedimentary rocks can melt. Igneous rocks can remelt. Metamorphic rocks can melt. Any of these metamorphic rocks or igneous rocks can go into sediment and become a sedimentary rock. It's kind of all mixed up and can go any way. And so depending on what part of the world you're in, you might see any parts of these or multiple parts, and they might be kind of converging into one area where you have metamorphic rock and sedimentary rock, or igneous rock and metamorphic rock. It just depends on where you're at. Okay, so as I said, they don't always go through the rock cycle in a nice cycle. A lot of igneous rocks do remain deeply buried, never become metamorphosed, never become sedimentary rocks. Sedimentary and metamorphic rocks may be uplifted and turned into other sediments. So you can have a sedimentary rock go through the sedimentary cycle multiple times and be eroded, turned into another sedimentary rock, eroded again, turned into another sedimentary rock, just kind of over and over. The rock cycle is kind of determined by Earth's processes. So you have the internal heat, you have the external processes like wind and rain and ice doing your weathering and erosion. And so it really, really depends on what part of the Earth the rock is in as to what's going to happen to it and how it's going to go through the rock cycle. So igneous rocks form when magma or lava cools and crystallizes. And I mentioned in the, sorry, the word left my brain. In the mineral section, that minerals grow, like the crystals grow, almost like we think of a plant growing. And so if you have a small tree, it's a young tree, more than likely, unless you're talking about bonsai, which is different. But if you have a small tree, it's a young tree. If you have a huge, like 100-foot, 200-foot tree, it's at least decades old, if not like over a century old. Crystals are kind of the same way. If you have a little tiny crystal that you need a microscope to see, it probably didn't take very long to cool and crystallize. If you have a nice big crystal, the quartz crystal that I have here is not a great example. If you have a nice big crystal, this took a long time to grow. This crystal did not come from igneous. This was not a cooled, like molten piece of silicate. This came from water processes, which we'll talk about later. But if you have a large enough crystal, it took a very long time to cool, and that can kind of tell you about the situation that the rock was in. In fact, let's go ahead and introduce some of these. Not like the rocks themselves, but just the image of cool versus fast. If I can here. Yeah, that's not too bad. And then I don't know if we have something perfect. This one isn't too bad. But yeah, these are almost like the same rock here. Get it out of the tray. Here we go. So I'm going to pass around these two. I'm going to turn the light on. And actually, I will hold these up for the camera. I don't know if this is going to work at all very well. So this rock is pretty much like a granite. I would call this a granite. You can see some of the colors. You can see some black specks. You can see some red specks. But they're pretty small. If you compare it to this one, which let me turn it where you can see not the sticker. If you compare it to this one, the one on your left, this one on your left has much bigger crystals. And so they took a longer time to grow. And you can kind of see both of these, small crystals versus big crystals. See, small crystals versus big crystals. And that's literally just the time it took to cool. So this one cooled quickly, this one cooled slowly. This one wasn't like super quick, but comparatively, this is the quick one, this is the slow one. And these crystals had a much longer time to grow, and so they formed bigger crystals in the rock, even though they're probably very similar composition-wise. This one's a little bit darker red, where this one has a little bit more pink in it. But they both have the white quartz, they both have the red feldspar, and the black hornblende. And so both of those would be granites. So this is basically based on what happens to your magma. Your magma is always generated underneath the surface. The energy comes from the core. It's melted because of gravity and because of pressure. So everything's pushing inward, which causes the rocks to heat up. You have molten material near the core at the mantle. The core is molten too, but that material never really rises up to the surface. But you have molten material in the mantle. It becomes hot. It becomes less dense. And due to convection generated by that heat, it rises to the surface. Oftentimes, most of the time, it does not make it all the way to the surface. It comes up, and then it gets stopped because you have a lot of rock to go through. Only in the rare instances where there's a weakness in the crust, there's cracks, or there's already like a lava tube from a previous volcano, does that magma get a chance to come all the way to the surface and erupt as a volcano. You got to get really close to the surface and then have a lot of pressure left over to be able to erupt up into the surface. Because as you come up, you're getting rocks that are cooler and cooler and cooler. So even, if you dig down like, I don't know what, but a couple thousand feet, maybe not a couple thousand feet, maybe just a couple, 2,000 feet doesn't sound that deep. If you dig down like 2,000 feet, the rocks aren't going to be hot. You're still going to have relatively cool earth. And so as that magma comes up, it encounters rocks around it and sediments around it that are much, much cooler than it is. And it does start to cool, and it kind of loses that upward motion. So, y'all all know this because we've been teaching all this from a young age. If it gets to the surface, it's called lava. If it stays underneath the surface, it's called magma. Now, when we get to the rocks that are formed by lava or magma, we have two different names for them. Extrusive is like the word exit. So extrusive got to the surface and erupted as lava. The opposite of that, which will be on the next page, is intrusive. If it never got to the surface, it stayed inside the earth and it cooled down there as magma. That is an intrusive rock. Both of these, just for your reference, are going to be intrusive. Even though this one has smaller crystals and it cooled faster than this one here, these would both be rocks that cooled below the surface and were not lava rocks. They were magma rocks. So we will talk about volcanoes. We'll actually have a whole separate chapter on volcanoes. So in this chapter, we're really just going to talk about the rocks that get formed by that. But know that when we talk about volcanoes, Hawaii, literally the entire existence of Hawaii is on a volcano. And so a lot of the terms surrounding volcanoes come from the Hawaiian language. Like we adopt their terms because they've been dealing with it for much longer than the rest of us have. We do have a lot of volcanoes here in the United States, although they're not super active. So we have the Cascades, the Columbia Plateau, which is actually a very a very big volcano. That I believe the Columbia Plateau and the Green River basalts are from the last Yellowstone supervolcano eruption. So we should see a map of that. If not, I will look it up real quick. So remember, I mentioned this already. Most magma never reaches the surface. It stays underground and it cools as a intrusive rock. So they call that intrusive or plutonic. And when they say plutonic, this is actually kind of interesting. Everybody's seen a lava lamp, right? When magma comes up from the surface, and let me do a terrible little drawing here. Here's your core, here's your mantle, and we have like this convection cycle where cool stuff goes down, hot stuff comes up just because of density. And then this is going to be exaggerated, so this isn't a great one, but here's your crust. And coming up from the mantle, you will get these plutons, and it literally looks like a lava lamp bubble. That's just the way that things flow. Physics doesn't really change for large things versus small things. And so if you have a less dense piece of material that's not really going to mix with the surrounding material, it's going to come up in a similar way, no matter whether it's like wax and water on a lamp or giant bubbles of molten rock coming up through non-molten rock that it's not really going to mix with. And so that is called a pluton. Has anybody ever been to what's it called? Enchanted Rock in Central Texas? Do you have? If you get a chance, if you're like making a trip through Central Texas, it's not really on the beaten path. There's not like a major highway or anything next to it. But if you happen to be down there and you see on the map that you're going to be near Enchanted Rock, take a stop. You don't even have to walk all the way to the top. Although if you do, you deserve a cookie because that is a. Did you go to the top? It's not a small walk. When you're down at the bottom, you're like, that's not that bad. And then you start to go up and you're like, wow, this is like incredibly steep and it's going to take me like an hour to get up there. But Enchanted Rock is one of these plutons. And what happened is it comes up through the surface. No, it doesn't come up through the surface. It came up under the surface. And so it's this giant kind of bubble. And then over time, weathering and erosion happens. It kind of takes all this top material and erodes it away. And what's left is this kind of land level. Because the igneous rock right here is very, very hard, resists weathering and erosion. The sedimentary rocks around it are not hard, and they don't resist as well. And so over time, that top layer has been eroded away, and you have this big intrusive pluton that's been exposed to the surface. The reason they call it enchanted rock is because it kind of has these like onion-like layers. I think it's pretty much done cooling. I'd be surprised if they say that they're still like molten in the middle. I don't think there is. I'm pretty sure it's done cooling. But because of these layers and all the cracks that happen, and you can even see where some of the layers have like cracked and slid off. In the summertime, well, probably any time of year, the sun heats it up and it gets hot. And these layers kind of expand, and then at nighttime it cools down and the layers contract. And this expanding and contracting make these like clicking sounds. They make really weird sounds. And so the Native Americans that lived in this area, at night you could hear the hill making these sounds, and that's why they call it Enchanted Rock, because it kind of had a feel like there were spirits in the rock kind of thing. Or at least that's the story that I've heard. And so that sound that you hear from the expanding and the cooling of the rock in the pluton lends its name to Enchanted Rock. But think of that, plutonic, think of Enchanted Rock, think of like the lava lamp bubble coming up. And really, in order for your intrusive rocks to be exposed at the surface, there has to be weather. Because they didn't come out as lava. They cooled and solidified underground, and you have to remove the layers on top of them in order for us to see them. Or, I guess the other way with mountains is you have to have that shoved up through the layers through like tectonic plate building. So most of our big mountain ranges, like the Rockies, the Appalachians on the East Coast, were due to two tectonic plates hitting each other, and you have that big mountain building kind of episode. Because when you think of the Rockies, it's a big mountain range, but it's not a volcanic mountain range. There's not volcanoes really associated with the Rockies. Where if you go into the Cascades, which is like Oregon, Washington, up into Canada, that mountain range is very much volcanic. Like there's all sorts of volcanoes along that. So they're kind of formed in two different ways. So they have some examples here. Mount Washington in New Hampshire was exposed by uplift and erosion. Stone Mountain in Georgia, Mount Rushmore in the Black Hills, and then Yosemite National Park in California. All of these are igneous, intrusive rocks that were exposed by uplift and erosion. Let's see. Okay. So I kind of mentioned this. Well, no, I didn't kind of mention it. I did mention it. The rate of cooling strongly influences how big your crystals are. If your crystals are big, it cooled very slow. If your crystals are very small or almost non-existent or microscopic, it cooled very fast, probably as lava at the surface, or even lava going into ocean water, which is going to cool it down even faster. How much time do we have? 10 minutes? 2 or 10?
10.
What?
So
we'll get y'all.
2.
Yeah, I guess 10. All right. So yeah, this instantaneous cooling, like if you have lava just dumped into the ocean, like you have it at Hawaii, you get no crystal growth. And literally, when you slice it open and look at the individual crystals, or try to look at the individual crystals under a microscope, you don't see any. It's almost down to the molecular level. There are no minerals. It's just a mixture of atoms. And so when you get something like volcanic glass, I've never really looked at ash, but I'm sure it's the same way. If you get that volcanic glass like obsidian, you can't determine what minerals are inside of it. It's literally impossible. The way to do it would be to dissolve it and figure out what chemical composition it has, and then you can kind of make a guess. But you won't be able to be like, this is quartz, this is feldspar, this is hornblende. That kind of stuff doesn't happen. Another thing crystallization is influenced by is dissolved gas. We call these volatiles, and we'll talk a little bit about that. But that's a little bit of a complicated topic, so I don't know that we'll get too deep into it in this class. So how do we describe an igneous rock? We call it the texture. The texture of the igneous rock, along with the composition, which texture is going to be your crystal size, and it does say shape, but we'll see. It's more going to be size and arrangement of your mineral grains. The other side to that is composition, which is what color they are or what minerals you think they are. And so composition is kind of what it's built out of. The texture is kind of how it's built. And so with texture of igneous rocks, size, shape, arrangement of those mineral grains, texture can be used to make inferences about a rock's origin. For example, if they're large crystals, we know it indicated as slow cooling. So it's probably an intrusive rock that never made it to the surface. If they're very small crystals, it can be fast cooling. And some rocks, which we'll talk about the name porphyritic in a little bit, have both. So it was underground, and it started to cool very slowly, and you get some crystals that are actually pretty big, and you can see them without the use of a microscope. And then all of a sudden you had uplift, or you had a huge erosion event, and the rest of the rock cooled very quickly. And so you have these larger crystals set in a smaller crystal matrix, and you see that there were two different cooling events. So it's not just slow or fast. You can have a fast and a slow in the same rock. So this is the fine grain texture. This is where your mineral grains are very small, which means it cooled very quickly, which probably is going to indicate a lava rock that happens. Now, if we're talking fine grain texture, in general terms, we mean something where you cannot see the individual grains with your eyes. You would have to use a microscope. If you just look at a rock like this, you're not going to be able to see like black specks and white specks and stuff like that. It'll just kind of all look gray or all look black or whatever. Sometimes it's kind of hard to tell because everything in nature exists on a spectrum instead of into nice, neat little categories. But in general, when we say fine grain texture, you would need the aid of a little magnifying glass or a microscope to be able to see those individual grains. So they say that here, individual crystals too small to see with the naked eye. They do have a subterm here, vesicular. Vesicular comes from the word vesicles. I'm trying to think of, well, veins aren't really the right term. But when I think of vesicular, I think of veins. And so vesicles are essentially little holes. So think of like pumice. Have any of y'all used pumice like in the bathroom to scrub your toes or whatever, your feet? It's all those little holes that help kind of scrape your dead skin away. That is actually a lava rock. Some of it is manufactured now, but still a lot of it is just a lava rock that they mine from volcanic areas. So if there's little gas bubbles that are trapped in there, they will leave those little holes and voids, and it will be vesicular. So it doesn't really matter what color it is or how you think it happened. If it has those holes in it, you're going to call it vesicular. And here's an example of that. You can see all the little holes in here in this lava rock, which means it was exposed to the surface very quickly. Have any of y'all taken welding class? When you weld, you have to have a shielding gas around your metal because metal doesn't like oxygen. Molten metal doesn't like oxygen. So if you just have regular oxygen getting to your metal pool when you're welding, it'll get bubbles and it'll spit and hiss and do all this stuff. The same thing happens to lava. They're not really metallic, at least most of them aren't, but they don't do well with oxygen. And so if they come to the surface and they're exposed to the air or to the water, very likely they will have bubbles in them and be vesicular. So then you get to coarse grained, and your coarse grained is essentially going to be your large grains. So you should be able to see the interlocking crystals with your naked eye. You shouldn't have to use a microscope or a magnifying glass. And that means it cools very slowly underground, insulated by the other rocks. Porphyritic is this term, and I don't really have a good explanation to help you kind of remember this name. But porphyritic means you had two different cooling events. You had a fast and a slow. Normally, I think the slow has to come first. I can't, off the top of my head, think of an example where you cool quickly and then cool slowly. But normally you have a slow cooling event for a time, and some crystals are allowed to build up pretty large. And then you have erosion or you have uplift, and your magma cools very quickly for the second part of it. And so you have these larger crystals in a fine-grained crystal matrix where you don't see any other large crystals. And then lastly, we have glassy. Glassy cooled almost instantly. This is going to be your lava that goes straight out of the ground and straight into the water, like in Hawaii. And literally on the atomic level, they freeze into place. There's no mineral creation. There's no crystal creation. Even when you slice a thin slice and look at it through a polarized microscope, you don't see any different mineral grains. It's just random atoms. And so we just call that glassy texture. And you'll see when we get to the chart that glassy can be pretty much any composition because it's really hard to figure out the composition of glassy minerals. So there are some trace minerals in here that they talk about. We'll move on. And this looks good. We'll leave this for tomorrow. Notice your lava lamp kind of protons coming up here. If they have a way to get to the surface, then you have your volcanoes. But if they don't, they will cool and solidify from the outward in, and you will have intrusive igneous rocks. So we'll leave this for tomorrow, and I will stop here. For the online people, I will try to figure out a way to get the labs going. Hopefully, we'll do that this week.